A telescope peers through 13 billion years of darkness. What it finds should not exist. Stars forged from nothing but the universe's first breath, hydrogen, helium, and a whisper of lithium. Giants burning 1,000,000 times brighter than our star, 10,000 times heavier, born before heavy elements poisoned the void. Objects so ancient their light has stretched across expanding space, arriving now as faint whispers from cosmic dawn. These are population 3 stars, the holy grail of astronomy, and they might finally be real. If you enjoy exploring the edges of what science knows, hit that like button and subscribe. Prepare yourselves, we begin. Light travels at 670 million miles per hour. Nothing in our universe moves faster. Yet even at this speed, the light reaching us tonight left distant objects billions of years ago. When you look at a star, you are not seeing it as it is. You are seeing its ghost, an image from the ancient past. The James Webb Space Telescope hovers 1 million miles from Earth, staring into darkness. Its mirror spans over 21 feet across, coated in gold so pure it reflects infrared light with almost perfect precision. This telescope does not search for planets or comets. It hunts for time itself. Every photon captured by its sensors is a messenger from epochs so distant that galaxies had barely begun to exist. Scientists aim this machine at a region called Max J 416. To the naked eye, nothing appears there, just empty blackness. Through Webb's instruments, that void explodes with detail. Hundreds of galaxies emerge, their light bent and stretched by 13 billion years of universal expansion. The further away an object sits, the longer its light has traveled. The longer light travels, the more the expanding universe stretches it from visible wavelengths into infrared. This is confirmed science. We measure this stretching effect and call it redshift. Higher redshift means greater distance. Greater distance means older light. LAP-1b, the target Webb discovered, has a redshift placing it at a distance of 13 billion light-years. When that light departed, our universe was only 800 million years old, barely 6% of its current age. Think about receiving a letter written before your grandparents were born. Now, multiply that timescale by billions. LAP-1b exists in an era called cosmic dawn, when the first stars ignited and began transforming the universe from a dark cloud of hydrogen into the glowing cosmos we recognize today. No human has ever directly observed this period. Every theory about how stars first formed comes from mathematics and simulation. Until now, those theories remained unproven. Scientists predicted what the first generation of stars should look like, how massive they should be, where they should form. But predictions mean nothing without evidence. Webb's detection of LAP-1b is not just another distant object. Early analysis suggests it might be the first confirmed sighting of population 3 stars, the universe's original furnaces, composed entirely of primordial elements. But here is where things become strange. These stars should have died long ago. Their fuel burns so hot and fast that most would collapse within a few million years. Yet we are seeing them now, frozen in time, their ancient light finally reaching our instruments. What Webb captured is not the stars themselves, but their echo, a photograph of ghosts that vanished from existence billions of years before Earth formed. The question scientists are now asking is simple and terrifying. If we found one cluster this ancient, how many more are hiding in the dark? Darkness reigned for 200 million years. After the Big Bang created space, time, matter, and energy, the universe cooled into a fog of hydrogen and helium. No stars existed, no galaxies. Just atoms drifting through expanding void, too hot to bond, too scattered to collapse. Then gravity began its patient work. Tiny density variations, quantum fluctuations, frozen into the fabric of reality during the Big Bang, created regions where gas was slightly denser. Matter attracted more matter. Dark matter invisible and impossible to detect directly, pulled at these clouds with its gravity. Slowly, over millions of years, the first structures assembled. Scientists call these early formations halos, dark matter halos, to be specific. These were not physical objects you could touch or see. Think of them as gravitational wells, invisible pits in space-time where normal matter began to pool. Hydrogen and helium fell into these wells, compressing under their own weight. As the gas compressed, it heated. As it heated, pressure built. Eventually, in the centers of the largest halos, temperatures climbed high enough for fusion to ignite. This is confirmed physics. When hydrogen atoms are forced together with enough energy, they merge into helium, releasing tremendous heat and light. This is how every star operates. But the first stars were different. Without heavy elements to help the gas cool efficiently, these primordial clouds could not fragment into many small pieces. Instead, they collapsed into singular, enormous masses. Population. 3 stars were born from this process. Theory predicts they formed approximately 200 million years after the Big Bang, though some simulations suggest they could have appeared even earlier. Their masses ranged wildly from 10 times our star's mass to potentially 1,000 times heavier. The biggest ones shone with the intensity of several million of our stars combined. These objects rewrote the universe's chemistry. Before they existed, the periodic table contained only 3 elements: hydrogen, helium, and trace amounts of lithium. Inside the cores of population, 3 stars, fusion created carbon, oxygen, nitrogen, iron, all the building blocks necessary for planets and life. When the most massive ones exhausted their fuel, they exploded as supernovae, scattering these new elements into space. Astronomers call this process metal enrichment, though metals in astronomy means any element heavier than helium. Every atom of carbon in your body, every oxygen molecule you breathe, every iron atom in your blood, all of it was forged inside stars. But those stars needed predecessors. Population 3 was the first generation, the original source, the cosmic factory that transformed a sterile universe into one capable of complexity. We have never seen one intact. Every star visible from Earth today belongs to later generations, already polluted with heavy elements. Population 3 vanished billions of years ago, their brief existences ending long before complex galaxies formed. Scientists have searched for decades, examining distant objects, analyzing spectra, hunting for that perfect signature of pure primordial composition. LAP-1b might finally be it. But to understand why this discovery is shocking, you need to know what should have made finding these stars impossible. Cosmology operates on rules. Gravity pulls matter together. Fusion ignites when cores reach 10 million degrees. Heavy elements change how gas cools and fragments. These are laws tested and confirmed over centuries of observation. According to those laws, certain objects should not appear at certain times. Yet James Webb keeps finding violations. Galaxies too massive for their age. Black holes too large to have formed so quickly. Bright objects in epochs that should contain only faint, primitive structures. LAP-1b is one of many recent discoveries forcing scientists to question whether our models of early universe evolution are incomplete. Here is the core problem. Standard cosmology predicts that galaxy formation was a slow process. Dark matter halos capture gas. Gas cools and collapses. Stars ignite. Those stars live, die, and scatter enriched material. New generations of stars form from that enriched gas, building up mass gradually over billions of years. This gradual assembly means early galaxies should be small, dim, and inefficient. Webb's observations contradict this prediction. In multiple surveys, astronomers have identified galaxies existing just 500 to 700 million years after the Big Bang objects that appear nearly as massive as our Milky Way. These are called red monsters, due to their reddish color and enormous stellar masses. One recent study found that some early galaxies converted gas into stars nearly twice as efficiently as their later counterparts. This is extremely confusing for theorists. Efficiency in star formation depends on how quickly gas can cool and collapse. Heavy elements help gas cool faster, which should make later galaxies more efficient, not less. Early galaxies had almost no heavy elements, which should have slowed their growth. Yet somehow they built themselves faster than physics predicted. LAP-1b adds another layer to this mystery. Population. 3 stars are not supposed to exist in isolation. Theory suggests they form in small clusters, a few thousand stellar masses worth, then quickly pollute their surroundings with metals from supernovae. After pollution begins, star formation should transition to the next generation. The window where pure population, 3 conditions exist is narrow, maybe a few million years. Finding one of these clusters requires looking at precisely the right moment in cosmic time. Too early, and even these first halos have not formed yet. Too late, and metal pollution has already corrupted the environment. LAP-1b sits at a redshift of 6.6, corresponding to roughly 800 million years after the Big Bang. This is on the late end of when scientists expect population 3 stars to appear. But here is what makes astronomers nervous. If LAP-1b is real, if it truly represents pristine population, 3 stars forming that late in cosmic history, it suggests these conditions persisted longer than models predict. That means the early universe might have hosted many more first-generation stars than previously thought. And if the universe produced more population 3 stars than expected, our entire understanding of how quickly metals spread and galaxies assembled might need revision. Skeptics remain cautious. Daniel Whalen, a researcher at the University of Portsmouth, has expressed doubt about several recent population 3 candidates. The evidence is strong, but not yet definitive. Spectroscopy can reveal composition, temperature, and motion, yet from 13 billion light-years away, even Webb's incredible sensitivity has limits. What astronomers need now is more data, more observations, more objects to compare. LAP-1b might be the first of many, or it might be an outlier, a cosmic fluke that tells us nothing about the broader picture. Either way, finding it was not luck. It required a trick Einstein predicted 100 years ago. Imagine holding a magnifying glass over an ant. The lens bends light, making the tiny creature appear larger. Replace the glass with a galaxy. Replace the ant with a star cluster 13 billion light-years away. This is gravitational lensing, and it is the only reason we can see LAP-1b. Albert Einstein predicted this phenomenon in 1915. His theory of general relativity states that massive objects warp the fabric of spacetime. Light traveling through warped spacetime follows curved paths. When a massive foreground object aligns with a distant background object, the foreground's gravity bends the background's light toward us, magnifying it. This is confirmed science. We have observed gravitational lensing thousands of times. Galaxy clusters, containing trillions of stellar masses worth of matter, create the strongest lensing effects. Max J 416 is one such cluster, sitting approximately 4 billion light-years from Earth. Behind it, far deeper in space, lies LAP-1b. When LAP-1b's light passes through the region around Max J 416, space-time curves. Some light that would have missed Earth entirely gets redirected toward us. The effect is dramatic magnification by a factor of roughly 100. Without this boost, LAP-1b would be invisible, too faint for even Webb's sensitive instruments to detect. Astronomers call this technique nature's telescope. It allows scientists to study objects that would otherwise remain forever beyond reach. But lensing does more than brighten. It also distorts. The magnified image often appears stretched into arcs or rings, called Einstein rings. The shape depends on the alignment and mass distribution of the foreground cluster. For LAP 1b, the geometry worked perfectly. The cluster's gravity focused light from the distant star cluster into a bright, measurable signal. Webb's near-infrared spectrograph captured this light and split it into its component wavelengths. What scientists saw in that spectrum told them something remarkable was happening. The spectrum showed intense emission lines from hydrogen. These lines appear when electrons in hydrogen atoms jump between energy levels, releasing specific colors of light. The strength and pattern of these lines reveal temperature, density, and composition. LAP-1b's hydrogen emission was extremely strong compared to its continuum, the background glow from stars themselves. This ratio is diagnostic. Young, hot, massive stars produce strong emission by ionizing the gas around them. That ionized gas glows brightly in specific wavelengths. Objects with very strong emission lines and weak continuum typically indicate a recent burst of star formation, with many massive, hot stars and very little older, stellar population. But there was something else. The spectrum also showed traces of carbon and oxygen, heavy elements that should not exist in pure population. 3 environments. This initially seemed like a problem. If heavy elements were present, could these really be first-generation stars? Scientists believe they have an answer. The heavy elements detected are extremely sparse, far below what later generation stars contain. This low metallicity suggests LAP-1b is catching the very beginning of metal pollution. Early supernovae or stellar winds from rapidly spinning massive stars have just started releasing their products. The environment is transitioning from pristine to enriched. Think of it like watching paint spread through water. For a brief moment, you see both clear water and colored regions mixing together. LAP-1b might represent that transitional instant where the first stars have begun altering their environment but have not yet fully polluted it. Without gravitational lensing, none of this analysis would be possible. The magnification did not just make LAP-1b visible, it made it bright enough for detailed spectroscopy. But even with perfect magnification and perfect instruments, one question remained. How do scientists know these are truly the first stars? The universe has 3 stellar populations. We live in an era dominated by population. 1 stars like our own, rich in heavy elements, forming planets, sustaining life. Older population, 2 stars contain fewer metals, dating back 10 billion years or more. Population 3 has never been directly observed, until possibly now. These populations are not arbitrary categories. They represent distinct generations, each with different chemical signatures. When astronomers look at a star's spectrum, they measure absorption lines, dark gaps, where specific wavelengths are blocked by elements in the star's atmosphere. Iron, carbon, oxygen, nitrogen. Each element absorbs light at characteristic wavelengths. Our star's spectrum shows rich absorption from dozens of heavy elements. Population. 2 stars show some metals, but at much lower concentrations. Population. 3 stars should show almost none. Just hydrogen, helium, and traces of lithium, the only elements produced by Big Bang nucleosynthesis. This distinction matters because composition determines how stars form and behave. Heavy elements act as coolants. When gas clouds collapse, compression generates heat. If that heat builds too quickly, pressure counteracts gravity and prevents further collapse. Heavy elements radiate heat away efficiently, allowing clouds to cool and fragment into many smaller pieces. Without heavy elements, primordial gas could not cool efficiently. Clouds collapsed into far fewer, far more massive objects. Computer simulations consistently predict that population 3 stars had typical masses between 10 and 1,000 times that of our star, with some models suggesting even higher masses were possible. These giants burned with extraordinary intensity. Fusion rates scale with mass. A star 10 times heavier than ours burns roughly 1,000 times brighter. A star 100 times heavier burns millions of times brighter. This means population. 3 stars exhausted their fuel rapidly. The most massive ones might have lived only a few million years before collapsing into black holes or exploding as supernovae. Their deaths seeded the universe with the first heavy elements. Carbon formed through triple alpha fusion, oxygen through carbon burning, silicon, sulfur, iron, created through successive fusion stages in the hottest cores. When the largest population 3 stars exploded, they scattered these elements across thousands of light years. Once metals contaminated the surrounding gas, conditions changed. The next generation of stars formed smaller and cooler. This is why population 3 stars should be rare and confined to the earliest epochs. The window where pristine conditions existed was brief. LAP-1b's spectrum shows exactly this scenario. Strong hydrogen emission indicates young, hot stars. Weak metal lines suggest minimal pollution. The detected oxygen and carbon concentrations match theoretical predictions for an environment just beginning to be enriched. Scientists estimate LAP-1b contains approximately 2,700 stellar masses worth of population, 3 stars, clustered in a region small enough that their combined supernovae are now polluting nearby gas. This makes LAP-1b precious. It is not just a fossil. It is a transition snapshot, capturing the exact moment when the universe shifted from its primordial state to a metal-enriched cosmos. Every star visible today, every planet, every living thing, our entire lineage traces back to moments like this. But the numbers seem impossible. LAP-1b sits 13 billion light-years away. Its stars are thousands of times heavier than ours. Their light has traveled across expanding space for most of cosmic history. How could they shine brightly enough for us to detect them? The answer lies in the intensity of their fire and the violence of their youth. Fusion is controlled detonation. Deep inside stellar cores, hydrogen atoms collide with such force that they overcome electromagnetic repulsion and merge into helium. This process releases energy photons and neutrinos that carry heat outward. The rate of fusion determines luminosity. More fusion means more light. Our star fuses roughly 600 million tons of hydrogen every second. This might sound enormous, but for a star, it is actually modest. Our star will burn for 10 billion years before exhausting its core fuel. Population: 3 stars had no such patience. Consider a population 3 star with 100 times the mass of ours. Its core pressure is not just 100 times higher, it is millions of times higher. Fusion rates scale steeply with temperature and density. A star 100 times more massive burns millions of times faster. This creates luminosity so intense that radiation pressure alone can blow away surrounding gas. Scientists estimate the brightest population, 3 stars, reached luminosities of 10 million times our star's output. To grasp this scale, imagine our star surrounded by 10 million copies of itself, all fusing simultaneously. That is how much light one first-generation giant produced. This extreme brightness has consequences. Photons carry momentum. When radiation floods outward from a stellar core, it pushes on surrounding material. For the most massive population, 3 stars, this radiation pressure became so strong it limited how large they could grow. Above a certain mass threshold, adding more gas simply gets blown away faster than it can accrete. Astronomers call this the Eddington limit. For normal stars, this limit sits around 150 stellar masses. Beyond that point, radiation overpowers gravity. Population: 3 stars might have pushed slightly higher due to their lack of heavy elements, but even they faced physical boundaries. Yet, within those boundaries, they achieved staggering feats. Their intense ultraviolet radiation ionized hydrogen across thousands of light years. This ionization is crucial. Before the first stars ignited, The universe was opaque, a fog of neutral hydrogen that blocked most light. As population 3 stars formed and shone, they carved out bubbles of ionized gas, creating transparent regions where light could travel freely. This process is called reionization, and it represents one of the most important phase transitions in cosmic history. Early universe, dark and opaque. Post-reionization universe, transparent and observable. Population. 3 stars were the primary drivers of this transformation, though later generations contributed as well. LAP-1b's spectrum confirms it is actively ionizing its surroundings. The strong hydrogen emission lines indicate gas being bombarded by intense ultraviolet radiation, stripping electrons from atoms. This ionized gas glows like a neon sign, marking the location of the hot, young stars responsible. But here is where theory makes a troubling prediction. Stars this massive and luminous should also be unstable. Their cores burn so hot that they produce photons with enough energy to spontaneously create matter-antimatter pairs. These pairs form briefly, then annihilate, releasing more energy. This process, called pair instability, can destabilize the star. For population, 3 stars in a specific mass range, roughly 140 to 260 stellar masses, pair instability leads to complete destruction. The star does not collapse into a black hole. It explodes entirely, leaving no remnant. Every atom of carbon, oxygen, and iron created in its core gets blasted into space. This means the brightest population 3 stars were also the shortest lived and most violent. They burned fast, died hard, and vanished completely. We see LAP-1b now because we are catching it during that brief window after ignition, before destruction. The clock is ticking. In cosmic terms, these stars have only moments left, but they were not alone in their violence. Nobody knows what dark matter is. We cannot see it, touch it, or detect it directly. Yet, we know it exists because we observe its gravitational effects. Galaxies rotate too fast for their visible matter alone to hold them together. Galaxy clusters contain far more mass than their stars and gas can account for. Cosmological models require dark matter to explain how structures formed. Scientists estimate dark matter comprises 85% of all matter in the universe. Normal matter atoms, molecules, everything we interact with makes up the remaining 15%. This ratio has remained constant since the early universe, though the distribution has changed dramatically over time. After the Big Bang, dark matter and normal matter began as nearly uniform distributions with tiny density fluctuations. Gravity amplified these fluctuations. Dark matter, which does not interact with light or normal matter except through gravity, collapsed first. It formed the scaffolding upon which normal matter would later build. Think of dark matter halos as invisible frameworks. They cannot emit light, so we do not see them directly, but their gravity attracts hydrogen and helium, pulling normal matter into dense concentrations. When enough gas accumulates in a halo, fusion ignites and a star is born. Without dark matter's gravitational wells, structure formation would have taken far longer. The first stars might not have appeared for billions of years instead of hundreds of millions. LAP-1b formed inside one of these early dark matter halos. Scientists estimate the halo mass at approximately 50 million times our star's mass. This is small compared to modern galaxy clusters, but large enough to trap gas and initiate star formation in the early universe. This mass estimate comes from models. Since we cannot see dark matter directly, astronomers use simulations that match observations. These simulations predict how dark matter clumps over time, how halos form, and where normal matter should accumulate. LAP-1b sits in a region and epoch consistent with these predictions for early halo formation. But dark matter did more than create the environment where LAP-1b formed. It also made the discovery possible through gravitational lensing. The galaxy cluster MAX-J 416, which magnified LAP-1b's light, contains enormous amounts of dark matter. Most of the cluster's mass is invisible. We infer its presence by observing how background light bends around it. Astronomers map dark matter distributions by analyzing lensing patterns. When many background galaxies appear distorted in similar ways, scientists can reconstruct the mass distribution of the foreground cluster. MAX-J 416 has been studied extensively for this purpose. Researchers know its dark matter content and can predict how it will lens objects at various distances. This prediction is what allowed scientists to estimate LAP-1b's magnification factor. The cluster amplifies its light by roughly 100 times. Without this boost, LAP-1b would be approximately 25 times fainter than Webb's detection threshold. Dark matter made the invisible visible, but gravitational lensing creates complications. Magnification is not uniform across the lensed image. Different regions get stretched by different amounts. This distortion makes it difficult to measure the true size and structure of LAP-1b. Scientists must carefully model the lensing effect and subtract it from observations to recover the object's actual properties. This process involves uncertainty. Small errors in estimating the cluster's mass distribution lead to errors in the inferred properties of lensed objects. This is one reason some astronomers remain cautious about declaring LAP-1b a definitive population 3 detection. The data is strong, but requires precise calibration. Still, the convergence is remarkable. Theory predicted where population 3 stars should form in low-mass dark matter halos. Observation found an object in exactly that environment. Theory predicted how massive these stars should be. Observation measures masses consistent with predictions. Theory said gravitational lensing could reveal these distant objects. Observation confirms this method works. Dark matter remains one of physics' greatest mysteries. We do not know what particles comprise it, or why it interacts so weakly with normal matter. But without it, the universe would be a structureless void. No galaxies, no stars, no planets, no life. LAP-1b owes its existence to dark matter, and we owe our knowledge of LAP-1b to dark matter's gravitational fingerprints. Yet confirmation requires more than elegant theory and single data points. Science advances through falsifiable predictions. A theory that cannot be tested is not science, it is speculation. For decades, astronomers have theorized about population 3 stars based on physics and simulations. Now they have 3 specific tests any candidate must pass. LAP-1b is the first object to pass all 3. Test 1. Environment. Population. 3 stars should form in low-mass, dark matter halos with specific properties. The halo must be massive enough to attract and trap hydrogen and helium, but not so massive that gas heats beyond the point where atomic cooling operates. This creates a narrow mass range, roughly 10 million to 100 million stellar masses worth of dark matter. Scientists call these atomic cooling halos. Hydrogen atoms can radiate energy through electron transitions, but only above certain temperatures. Below those temperatures, gas remains too hot to collapse. Above them, gas cools rapidly and star formation becomes efficient. Early universe halos that fell into this sweet spot were prime sites for population 3 formation. LAP-1b sits in a halo estimated at 50 million stellar masses. This places it squarely in the predicted range. Previous population, 3 candidates failed this test. They required far more massive halos, sometimes 1 million times heavier, to explain their observed brightness. This inconsistency made those candidates suspect. Test 2. Initial mass function. Stars do not form with random masses. They follow a distribution called the initial mass function, which describes how many stars form at each mass. For population, 3 stars, Simulations predict a logarithmically flat distribution over a massive range, roughly 10 to 1,000 stellar masses. This is very different from modern star formation, which produces mostly low-mass stars. The reason comes back to cooling. Without heavy elements, primordial gas could not fragment efficiently. Most of the collapsing cloud went into a single massive object rather than breaking into many smaller pieces. LAP-1b's spectrum supports this prediction. The ratio between specific emission lines indicates a stellar population dominated by massive objects. If LAP-1b contained many small stars, the emission line ratios would look different. The observations match what scientists expect from a top-heavy mass distribution. Test 3. Stellar mass and pollution. Population. 3 stars form in small clusters with total masses of a few thousand stellar masses before self-polluting. As the first supernovae explode, they enrich surrounding gas with metals. This pollution should appear as weak but detectable metal lines in the spectrum, exactly what LAP-1b shows. The measured metal abundances are extremely low, consistent with enrichment from just a handful of supernovae. Carbon and oxygen appear in ratios predicted by population 3 supernova models. The cluster's total stellar mass, estimated from hydrogen emission strength, sits at approximately 2,700 stellar masses. This matches theoretical expectations for when pollution should begin. Previous candidates failed one or more of these tests. Some showed too much metal enrichment, indicating they were not truly pristine. Others required stellar populations far more massive than simulations predict. A few had spectral properties inconsistent with hot young stars. LAP-1b passes all 3. This convergence is what makes it compelling. No single test is definitive. Spectroscopy, from 13 billion light-years away, carries uncertainties. Lensing models have error bars. Theoretical predictions depend on assumptions about dark matter and gas physics. But when multiple independent tests all point to the same conclusion, confidence grows. Scientists call this triangulation. If you measure a mountain's height from one angle, you might be wrong. If you measure from 3 angles and get consistent results, you are probably right. LAP-1b has been measured from multiple angles. Each measurement supports the population 3 hypothesis. This does not mean the case is closed. Confirmation requires follow-up observations, preferably from multiple instruments. Other research groups will analyze the same data and check the conclusions. This is how science works. Claims require evidence. Evidence requires verification. Verification requires time. But if LAP-1b holds up, it opens the door to finding many more. And then the real work begins. Chemistry constrains structure. The elements available determine what can form. In a universe containing only hydrogen and helium, complexity remains limited. No carbon-based molecules, no oxygen to form water, no silicon for rocks. Just the 2 simplest elements, drifting through expanding space. This simplicity shaped the first stars. When primordial gas clouds collapsed, they could not cool below certain temperatures. Molecular hydrogen formed 2 hydrogen atoms bonded together, and this molecule radiated energy through vibration and rotation. This cooling allowed clouds to contract slowly, building up mass at their centers. Without heavy elements to carry heat away efficiently, these contracting cores remained hot and diffuse. Gravity continued pulling inward. More gas fell into the potential well. Eventually, the accumulated mass became so large that a single central object formed rather than many small fragments. Computer simulations have tracked this process in detail. Researchers start with initial conditions matching the early universe, a slightly overdense region of hydrogen and helium in a dark matter halo. They let physics evolve the system forward. Gravity pulls, gas heats, cooling mechanisms operate, turbulence develops. The simulations consistently show that the first collapsing cores reach masses between 10 and 1,000 times our star's mass. A typical population 3-star might weigh 100 to 300 stellar masses. This is enormous compared to modern star formation, where the average new star weighs less than half our star's mass. Why such a difference? The answer lies in opacity and feedback. In modern star-forming regions, dust grains absorb starlight and re-radiate it as infrared. This heats surrounding gas, creating pressure that opposes further collapse. Additionally, stellar winds and supernova explosions from already formed stars disrupt nearby clouds, preventing them from accumulating too much mass. Population 3 environments lacked both mechanisms. No dust existed yet because dust forms from heavy elements. No previous generation of stars existed to provide disruptive feedback. Collapsing clouds faced minimal resistance. They grew until radiation pressure from the forming star itself became strong enough to halt further accretion. LAP-1b likely contains several of these giants. The total cluster mass of 2,700 stellar masses could consist of a few dozen stars, averaging 100 stellar masses each, or a handful of supermassive stars exceeding 500 stellar masses. Current observations cannot distinguish between these scenarios because individual stars remain unresolved. We see the cluster as a single bright point. These monsters lived fast. Fusion rates scale with mass to roughly the 4th power. A star 10 times heavier burns 10,000 times faster. A star 100 times heavier burns 100 million times faster. This means a population 3-star weighing 100 stellar masses might exhaust its hydrogen fuel in just 1 million years. For comparison, our star will fuse hydrogen for approximately 10 billion years. Population 3 stars burn through their fuel 10,000 times faster. They were cosmic mayflies, brilliant but brief. When they died, the manner of death depended on mass. Stars below roughly 40 stellar masses likely collapsed into black holes after exhausting their fuel. Stars between 40 and 140 stellar masses exploded as core collapse supernovae, scattering enriched material. Stars between 140 and 260 stellar masses experienced pair instability supernovae, destroying themselves completely. The most massive stars, above 260 stellar masses, might have collapsed directly into black holes without exploding. Their gravity became so intense that even supernova energy could not overcome it. These direct collapse scenarios could have produced intermediate mass black holes, weighing hundreds of stellar masses, rare objects that scientists have only recently begun detecting. LAP-1b's metal pollution suggests at least some of its stars have already died as supernovae. The carbon and oxygen detected in its spectrum had to come from stellar interiors. This means we are witnessing the cluster during its death throes, as the first supernovae enrich the environment and the remaining giants continue burning. Soon, on cosmic timescales, the entire cluster will go dark. But darkness was not the only possibility for these ancient giants. Stellar death is orderly. Fusion proceeds through predictable stages, each requiring higher temperatures. Hydrogen fuses into helium, helium fuses into carbon and oxygen, carbon fuses into neon and magnesium, oxygen fuses into silicon and sulfur, silicon fuses into iron, then fusion stops. Iron cannot be fused into heavier elements while releasing energy. Physics forbids it. Iron sits at the peak of the nuclear binding energy curve. Fusing iron into heavier elements requires adding energy rather than releasing it. Once a star's core converts to iron, fusion ceases. The core no longer generates pressure to counteract gravity. Collapse becomes inevitable. For population 3 stars, this progression happened quickly. Their immense masses created core temperatures and pressures far beyond what smaller stars experience. Fusion stages that take millions of years in lower mass stars happened in days or weeks for the giants. A population 3 star weighing 200 stellar masses might burn through hydrogen in 1 million years, helium in 10,000 years, and heavier elements in mere months. The final stages accelerate dramatically. Silicon burning, the last fusion stage before iron core formation, produces iron on timescales of days. The star's core grows rapidly, accumulating iron until it reaches a critical mass called the Chandrasekhar limit. Above this limit, electron pressure cannot support the core against gravity. Collapse happens in less than 1 second. The core shrinks from the size of Earth to roughly 12 miles across. This releases gravitational energy equivalent to roughly 100 times what our star will produce over its entire lifetime. Most of this energy emerges as neutrinos, ghostly particles that barely interact with matter, but about 1% gets deposited into the surrounding stellar layers. That 1% is enough. The outer layers explode outward at 10% the speed of light. This is a core collapse supernova, one of the most energetic events in the universe. The explosion synthesizes elements heavier than iron through rapid neutron capture, creating gold, platinum, uranium, and other heavy elements. Everything then gets blasted into space. Population: 3 supernovae operated similarly but with crucial differences. Their progenitor stars contained no heavy elements, which affected the explosion mechanism. Computer models suggest population 3 supernovae were extremely energetic, with explosion energies up to 10 times higher than modern supernovae. This enhanced energy came from rotation. Population 3 stars likely formed with high angular momentum because the clouds they collapsed from had not yet dissipated energy through multiple fragmentation events. Rapidly spinning cores can tap rotational energy during collapse, boosting explosion power. Some models predict the fastest rotating population 3 stars produce jets rather than spherical explosions, focusing energy along the rotation axis. LAP-1b shows evidence of this explosive activity. The oxygen and carbon detected in its spectrum were synthesized inside stellar cores and ejected by supernovae. The amounts measured are consistent with enrichment from a small number of explosions, perhaps 3 to 7, depending on the masses of the progenitor stars. This metal pollution is both confirmation and problem. It confirms stars have formed and died in LAP-1b, validating the population 3 hypothesis, but it also means the environment is transitioning. Give it another million years, and the surrounding gas will become too enriched to form pure population 3 stars. Future star formation will produce population 2 objects instead. We are seeing LAP-1b at the perfect moment, early enough that most stars remain pristine, but late enough that first deaths have begun. This timing is not coincidental, it is selection bias. Objects in this transitional phase are easiest to detect because they produce strong emission from both pristine stars and supernova-enriched gas. Pure population, 3 clusters before any deaths occur, might be even fainter. Fully enriched regions look like normal early galaxies. The sweet spot, where both signatures appear, is narrow. LAP-1b hit that sweet spot. But some scientists think the first stars might not have died at all. Dark matter is strange. It passes through normal matter like a ghost. Trillions of dark matter particles likely flow through your body every second without interacting. Yet gravitationally, dark matter dominates the universe. Its invisible hand shapes galaxies, bends light, and determines cosmic structure. One leading theory proposes dark matter consists of weakly interacting massive particles, known as WIMPs. These hypothetical particles would have significant mass but interact with normal matter only through gravity and possibly the weak nuclear force. If WIMPs exist, they have one peculiar property: they can annihilate each other. When 2 WIMPs collide, theory predicts they destroy each other, converting their mass into energy. According to the equation, energy equals mass times the speed of light squared. This annihilation releases tremendous heat. In most regions of space, dark matter is too diffuse for annihilation to matter. But in the dense cores of collapsing gas clouds, dark matter particles might cluster tightly enough for annihilation to become significant. Catherine Fries, an astrophysicist at the University of Texas, first proposed in 2007 that this process could power a new type of star. She called them dark stars. These objects would look like stars, giant balls of glowing hydrogen and helium, but their energy source would be dark matter annihilation rather than fusion. This is speculative theory, not confirmed science. Nobody has detected a dark star. Nobody has even proven WIMPs exist. Dark matter might consist of entirely different particles that do not annihilate. But if dark stars are real, their signatures would be distinctive. Dark stars could grow far larger than fusion-powered stars. Radiation pressure from fusion limits normal stars to a few hundred stellar masses. Dark matter annihilation produces heat more gently, without the intense radiation pressure. This would allow dark stars to accumulate thousands or even millions of stellar masses while remaining stable. These giants would shine with incredible brightness but appear cooler than fusion stars. Their surface temperatures might reach only 10,000 degrees instead of 50,000 degrees, typical for massive hot stars. This temperature difference produces a characteristic spectrum, very bright in infrared, but relatively dim in ultraviolet. Recent James Webb observations have identified several objects that might fit this description. 3 candidates designated JADESGS Z130, Z120, and Z110 show properties consistent with supermassive dark stars. They appear at redshifts, placing them 300 to 400 million years after the Big Bang. Their spectra suggest surface temperatures and luminosities matching dark star predictions. If confirmed, dark stars could solve multiple puzzles. First, they might explain how supermassive black holes formed so early. These objects, weighing millions or billions of stellar masses, appear in the first billion years of cosmic history. Standard formation mechanisms struggle to build such massive black holes that quickly. But if dark stars could reach millions of stellar masses, they could collapse directly into large black holes when their dark matter fuel depleted. Second, dark stars might reconcile an apparent overabundance of massive early galaxies. Webb has found more bright, massive objects in the early universe than simulations predicted. If some of these objects are actually individual dark stars rather than entire galaxies, the abundance would match theoretical expectations better. LAP-1b does not appear to be a dark star. Its spectrum shows characteristics of hot fusion-powered stars rather than cooler dark stars. But the possibility remains that some population 3 environments hosted both types of objects. Early dark matter halos might have assembled enough dark matter for annihilation heating, while simultaneously collapsing gas for fusion. This dual-source scenario has not been modeled in detail. It represents frontier research where observations have moved faster than theory. Scientists are now working to understand whether dark matter annihilation could have meaningfully affected early star formation, even if it did not power entire stars. The question matters because dark matter remains mysterious. Detecting dark stars would provide the first direct observation of dark matter particles beyond their gravitational effects. It would tell us what dark matter is, how it interacts, and whether our theories about particle physics are correct. For now, dark stars remain possibilities, not certainties. They exist in simulations and equations. Whether they exist in reality depends on observations that are still being analyzed. But population, 3 stars, fusion-powered or not, faced another problem. They appeared too early and too bright. Black holes form from collapse. When a massive star exhausts its fuel, its core implodes under gravity. If the core mass exceeds roughly 3 times our star's mass, Nothing can stop the collapse. Electrons and protons merge into neutrons. Neutrons compress into quark matter. Eventually, matter disappears beyond the event horizon, the point where escape velocity exceeds light speed. This creates stellar mass black holes weighing a few to a few dozen stellar masses. They are common. Astronomers have detected thousands through gravitational waves and X-ray emissions. These objects form quickly within milliseconds of core collapse, but they start small. Supermassive black holes are different. They weigh millions or billions of stellar masses. Our galaxy hosts one at its center, weighing roughly 4 million stellar masses. Observations suggest every major galaxy contains a central supermassive black hole. The masses correlate with galaxy properties, implying black holes and galaxies grew together. Standard models predict supermassive black holes form gradually. A stellar mass black hole seeds the process. Material from surrounding stars and gas falls in, adding mass. Each time the black hole doubles its mass, it must accrete an amount equal to its current mass. Even if material flows in at the maximum possible rate called the Eddington limit, this process takes hundreds of millions of years. Quasars, extremely bright objects powered by supermassive black holes actively feeding, have been observed at redshifts above 7. This places them less than 700 million years after the Big Bang. Some black holes at these epochs weigh over 1 billion stellar masses. Formation timescales become problematic. Starting from a stellar mass seed and growing at maximum accretion rates, black holes can double in mass every roughly 50 million years. To reach 1 billion stellar masses in 700 million years requires growing by a factor of approximately 1,000. This demands 30 doublings, taking 1.5 billion years at maximum rates. The math does not work. These supermassive black holes existed before they had enough time to grow through standard mechanisms. Either they formed with much larger seed masses, or they grew faster than physics should allow, or our models are wrong. Population. 3 stars might provide the solution. If the most massive population 3 stars collapsed directly into black holes without exploding, they could create intermediate mass seeds weighing hundreds to thousands of stellar masses. Starting from these larger seeds, black holes could reach supermassive status more quickly. Dark stars offer another possibility. If dark matter annihilation allowed stars to reach masses of hundreds of thousands or even millions of stellar masses before collapsing, they could leave behind massive black hole seeds. A million stellar mass dark star collapsing into a black hole would only need to double its mass 10 times to reach 1 billion stellar masses. This requires only 500 million years at maximum accretion rates, comfortably fitting within observed timescales. Recent observations support these scenarios. Some early supermassive black holes show unusual properties suggesting rapid growth or large seeds. Their host galaxies often appear smaller and less massive than expected, indicating the black holes formed earlier in the galaxy assembly process. LAP-1b might be witnessing this process in action if its population. 3 stars are extremely massive, several hundred to 1,000 stellar masses. Their eventual collapse could create intermediate mass black holes. Over the next billion years, these seeds could grow into the supermassive black holes we observe at later epochs. But there is another complication. Recent surveys have found tiny, extremely bright objects in the early universe that do not fit any simple model. Astronomers call them little red dots because of their appearance and color. Some might be small galaxies, others might be black holes. A few could be something entirely new. One radical proposal suggests little red dots are black hole stars, entire stellar populations, compressed around central black holes into objects far denser than normal galaxies, but not quite collapsed into single black holes. These hypothetical structures would represent an intermediate stage between star cluster and supermassive black hole. If black hole stars exist, they could form directly from population 3 clusters. As the first stars die and leave black hole remnants, those remnants orbit within the cluster. Dynamical friction causes them to spiral inward and merge, creating a central, massive black hole. Meanwhile, ongoing star formation adds more mass to the system. The result: a hybrid object containing both stars and a growing central black hole. This scenario remains speculative. Current observations lack the resolution to confirm whether little red dots are truly this exotic. But the fact that astronomers are proposing such radical ideas shows how much Webb's discoveries have challenged conventional thinking. The early universe was not supposed to look like this, but it did, and it keeps getting stranger. Star formation requires gas. Galaxies form stars by converting hydrogen into stellar mass. Observations of nearby galaxies show conversion efficiency around 20% or less. For every 100 units of gas mass in a galaxy, roughly 20 become stars. The rest gets blown out by stellar winds, remains as unconverted gas, or never participates in star formation. This low efficiency reflects physics. Stars inject energy into their surroundings through radiation, winds, and supernovae. This energy heats gas, stirring turbulence and opposing gravitational collapse. Heavy elements help by radiating energy away, allowing gas to cool and collapse more easily. But even with metals present, much gas never forms stars. Early galaxies should be even less efficient. With minimal heavy elements, gas cools slowly. Fewer collapsing clouds means fewer stars. Theoretical models predicted early galaxies would convert only 5 to 10% of their gas into stars, taking billions of years to build substantial stellar masses. In November 2024, an international team announced discovery of 3 red monster galaxies. These objects appear at redshifts, placing them roughly 600 to 800 million years after the Big Bang. Spectroscopic measurements revealed stellar masses comparable to our present-day Milky Way, between 100 billion and 300 billion stellar masses. The problem is timing. To accumulate that much stellar mass that early requires converting gas into stars at nearly 50% efficiency. This is more than twice what models predicted. The galaxies somehow built themselves far faster than physics seemed to allow. The name red monsters comes from their appearance. They glow brightly in infrared but appear faint in shorter wavelengths, giving them a reddish color in Webb's images. This color indicates heavy dust content. Dust forms from heavy elements produced by stars, then cools to emit infrared radiation. Large dust quantities suggest significant star formation has already occurred. Scientists remain puzzled about how these galaxies formed so much dust so quickly. Dust production requires supernovae to create heavy elements, followed by dust grain condensation in cool environments. Both processes take time, typically hundreds of millions of years in modern galaxies. Red monsters somehow accelerated this timeline dramatically. One possibility involves extremely bursty star formation. Instead of steady conversion of gas into stars, perhaps these galaxies experienced brief episodes of intense star formation, converting large fractions of their gas during short bursts. Computer simulations show this can happen if gas accumulates over long periods, then collapses rapidly when conditions become favorable. Another explanation invokes dark matter feedback. Perhaps early dark matter halos had properties that enhanced gas cooling or reduced turbulence, allowing more efficient star formation. This would require revision of dark matter models, but observations are forcing theorists to consider possibilities previously dismissed. Red monsters also show unusual structures. Unlike mature galaxies with smooth distributions of stars, these objects appear clumpy, with multiple bright knots of star formation. This suggests they have not yet settled into stable configurations. They are still assembling, with gas flowing in from surrounding regions and colliding to trigger starbursts. LAP-1b might represent an even earlier stage of this process. Its stellar mass of 2,700 stellar masses is tiny compared to red monsters, but it sits at a slightly earlier epoch. If LAP-1b grows over the next few 100 million years, accumulating gas and forming new generations of stars with increasing efficiency, it might eventually resemble a red monster. This evolutionary picture is appealing but unproven. The connection between population, 3 clusters like LAP-1b, and massive galaxies like red monsters remains speculative. Many intermediate steps must occur. Dark matter, halos must grow, gas must flow in, supernovae must enrich the environment, new star formation must begin. Each step introduces uncertainties. Not every population, 3 cluster, will evolve into a massive galaxy. Some might remain small, their star formation quenched by feedback. Others might merge with neighbors, forming larger structures through collision rather than steady growth. What is certain is that Webb has revealed more diversity in the early universe than anyone expected. Galaxies formed in many ways, at many times, with wide variation in properties. Simple models predicting gradual, orderly assembly clearly miss important physics. The challenge now is figuring out what that missing physics is, and that requires finding more objects, more data, more pieces of the puzzle. Redshift is measurable. When light travels through expanding space, its wavelengths stretch. Visible light shifts toward redder colors. Eventually, red light stretches into infrared. Infrared stretches into mid-infrared. The farther light travels, the more it stretches. Astronomers exploit this stretching to measure distances. They take images of the same region through filters that pass only specific wavelength ranges. Nearby galaxies appear bright in all filters. Distant galaxies appear bright in some filters, but completely dark in others. This darkness is diagnostic. Consider a galaxy at redshift 7. The ultraviolet light it emitted has been stretched into visible wavelengths by the time it reaches us. Visible light has stretched into near-infrared. Infrared has stretched into mid-infrared. If we observe this galaxy through a filter designed to detect visible light, we see the stretched ultraviolet emission. If we observe through an ultraviolet filter, we see nothing. The galaxy's ultraviolet light has shifted out of that filter's range. This technique is called the dropout method. A galaxy that appears in long wavelength filters but drops out of short wavelength filters must be extremely distant. The dropout point tells us the galaxy's redshift. The brightness in remaining filters tells us its luminosity and mass. Webb's cameras have been optimized for this technique. The near-infrared camera covers wavelengths from roughly 0.6 to 5 microns. The mid-infrared instrument extends from 5 to 28 microns. Together, they can detect galaxies at redshifts beyond 15, corresponding to light emitted less than 300 million years after the Big Bang. One recent survey used this method to identify 300 candidate early galaxies. Researchers at the University of Missouri analyzed Webb images looking for objects bright in mid-infrared but dark in shorter wavelengths. Each candidate underwent follow-up analysis to estimate its redshift and properties. Many turned out to be farther and brighter than expected. Some showed redshifts above 10, placing them in the first 500 million years of cosmic history. Their luminosities suggested either extremely efficient star formation or exotic power sources like active black holes. LAP-1b was not found through the dropout technique. It was identified through gravitational lensing surveys targeting known massive galaxy clusters. But dropout surveys complement lensing by finding objects in random fields rather than only in regions with strong magnification. This gives a more representative sample of the early universe. The two methods have different strengths. Lensing finds extremely faint objects by boosting their brightness, but only in specific locations. Dropout surveys cover wider areas, but miss objects too faint to detect without magnification. Combining both approaches gives the most complete picture. Dropout candidates require confirmation. Initial identification comes from colors alone, the pattern of which filters show detections versus dropouts. This can produce false positives if dust or unusual spectra mimic high redshift signatures. Follow-up spectroscopy provides definitive redshifts by measuring specific emission or absorption lines. Webb has now obtained spectra for hundreds of dropout candidates. Most have confirmed as genuine high redshift galaxies. A few turned out to be dusty, lower redshift objects masquerading as distant galaxies. This confirmation rate is high enough to trust statistical studies based on dropout samples. Those statistical studies are revealing surprising patterns. Early galaxies appear more abundant than models predicted. Their luminosity function, the number of galaxies at each brightness level, exceeds theoretical expectations by factors of 2 to 5. Either star formation was more efficient than models assume, or some galaxies contain exotic power sources boosting their brightness. LAP-1b contributes to understanding this abundance. It represents the earliest phase of star formation, population. 3 stars just beginning to enrich their environment. Knowing how many objects like LAP-1b exist tells us how much early star formation involved pure primordial stars versus later generations. If population 3 formation was common, many early galaxies might have gone through this phase. If rare, most galaxies skipped directly to metal-enriched star formation. Current observations suggest population 3 clusters are uncommon but not extremely rare. Perhaps 1 in 100 early galaxies shows signatures consistent with pristine stars. This rate has implications for metal enrichment. If most galaxies never host population 3 stars, where did their metals come from? Either a few massive population, 3 supernovae, scattered metals across large volumes, or metals formed through other channels scientists have not yet identified. The answers will emerge as Webb continues finding and characterizing distant objects. But even with hundreds of candidates identified, one mystery deepens. Luminosity has limits. Stars shine by converting mass to energy. The conversion efficiency is approximately 0.7% for every 1,000 kilograms of hydrogen fused. 7 kilograms convert to energy. This energy emerges as photons that carry away the stellar luminosity. Given this efficiency, calculating stellar luminosity from mass is straightforward. A galaxy containing 100 billion stellar masses worth of stars can produce roughly 10 billion times our star's luminosity, assuming the stars have average masses similar to ours. Massive stars produce more light per unit mass, but stellar populations tend to have more low-mass stars than high-mass stars, averaging out to predictable values. Early galaxies should be dim. With lower stellar masses and potentially fewer massive stars, their luminosities should fall below later galaxies. This is what models predicted. This is not what Webb found. Of the 300 candidate early galaxies identified in recent surveys, many shine brighter than galaxies 10 times their stellar mass at later epochs. Some appear as luminous as modern massive galaxies, despite containing only 1/10 the stellar mass. This brightness excess cannot be explained by conventional star formation alone. Several explanations have been proposed. First, perhaps these galaxies contain unusually high fractions of massive stars. Top-heavy stellar populations produce more light per unit mass because massive stars burn brighter. This could boost luminosity by factors of 2 to 3 beyond expectations. Second, active black holes might contribute significant light. If every early galaxy hosts a feeding supermassive black hole, emission from hot gas spiraling into those black holes could dominate total luminosity. This would make small galaxies with modest stellar masses appear as bright as much larger systems. Third, some objects might not be galaxies at all. They could be individual supermassive dark stars, if those exist shining with the luminosity of millions of normal stars. A single dark star weighing a few million stellar masses could appear as bright as a small galaxy. Fourth, measurement errors might inflate apparent luminosities. Gravitational lensing, dust extinction, emission line contamination, multiple effects can bias photometric measurements. If some candidates are actually less luminous or less distant than initially estimated, the brightness excess disappears. Current evidence suggests all four factors play roles. Some bright candidates have confirmed as active black holes based on spectroscopy. Others show evidence of top-heavy stellar populations or significant dust. A few have been reanalyzed and found to be lower redshift objects with misidentified redshifts, but even accounting for these corrections, an excess remains. There are too many bright early galaxies. Standard models must be revised. One revision involves adjusting star formation efficiency. If early galaxies converted gas into stars at 30 to 50% efficiency, instead of the assumed 10 to 20%, they could build stellar masses faster and appear brighter earlier. This matches observations of red monsters and other massive early galaxies. Another revision concerns black hole formation. If supermassive black holes formed more easily or grew faster than models predict, their contribution to early galaxy brightness could account for some excess. This requires either larger seed masses or more efficient accretion, both of which population 3 stars or dark stars could provide. A third revision questions dark matter properties. If dark matter halos in the early universe had slightly different distributions or concentrations than assumed, gas would cool and collapse differently. This could accelerate structure formation and allow earlier, more efficient star formation. LAP-1b provides constraints on these revisions. Its stellar mass and luminosity match expectations for a population 3 cluster without requiring exotic physics. This suggests conventional processes can produce early objects when conditions are right. The question is whether LAP-1b represents typical or exceptional circumstances. Statistics favor typical. If LAP-1b were extremely rare, finding it within the limited area covered by Webb surveys would be unlikely. The fact that it was discovered suggests similar objects exist throughout the universe. Scaling up observed number densities, astronomers estimate thousands of population. 3 clusters might exist within Webb's reach. This creates both excitement and challenge. Excitement because finding many population 3 clusters would enable statistical studies revealing how these objects formed, evolved, and influenced their surroundings. Challenge because confirming each candidate requires expensive spectroscopic follow-up observations. Webb's schedule is oversubscribed. Allocating time to study hundreds of faint objects competes with other scientific priorities. Priorities must be set. Which candidates deserve follow-up? Which questions matter most? Should resources focus on confirming many objects at low detail, or studying a few objects in great depth? These decisions shape the future of early universe research. But one class of objects already demands attention. Galaxies have structure. Stars orbit a central bulge. Gas flows through spiral arms or settles into disks. Dark matter forms an extended halo, providing gravitational scaffolding. This organization emerges from billions of years of evolution mergers, accretion, feedback cycles that shape galactic architecture. Early galaxies should be messier. Simulations predict they appear clumpy and irregular, with multiple bright knots of star formation and chaotic gas distributions. As time passes and systems settle, smooth structures emerge. By looking at galaxies at different epochs, astronomers trace this evolutionary sequence from chaos to order. Little red dots do not fit this picture. They appear as tiny, compact objects, often less than 1,000 light-years across, shining with luminosities comparable to entire galaxies. Their sizes suggest they contain stellar densities hundreds of times higher than normal galaxies, yet their colors indicate they formed stars recently, contradicting expectations that compact objects should be old and dead. Discovered in James Webb's deep field images, little red dots have sparked intense debate. Are they galaxies? Black holes? Something new? Their properties resist simple classification. Spectroscopic analysis reveals complex spectra with both stellar signatures and emission lines characteristic of active black holes. This dual nature suggests these objects contain both stars and feeding supermassive black holes in extremely compact configurations. The black holes often weigh hundreds of millions to billions of stellar masses, comparable to black holes in much larger modern galaxies. This creates a puzzle. How did such massive black holes form in such small systems so early? Black hole masses typically correlate with host galaxy masses. Little red dots violate this correlation, hosting disproportionately massive black holes in undersized galaxies. One possibility is that little red dots are not galaxies, but black hole stars, hypothetical structures where an entire stellar cluster orbits tightly around a central black hole. The black hole grows by accreting stars and gas from its surroundings. Meanwhile, the stellar cluster continues forming new stars from infalling material. The result is a hybrid object, denser than a galaxy, but more extended than a single star. If this interpretation is correct, little red dots might represent a transition phase between population 3 clusters like LAP, 1b, and mature galaxies with central black holes. As the population 3 stars die, they leave black holes that merge, creating a massive central object. Ongoing star formation adds new stellar populations around this core. Eventually, the system expands and settles into a recognizable galaxy morphology. This evolutionary sequence remains speculative. Confirming it requires observing many objects at different stages and identifying trends in properties versus cosmic time. LAP-1b and little red dots might represent beginning and middle phases of a process that ultimately produces normal galaxies. Alternatively, little red dots might be entirely separate phenomena, unrelated to population 3 formation. Perhaps they form through direct collapse mechanisms, where gas clouds implode into supermassive black holes without ever forming stars. The surrounding stellar component would then form later from material accreting around the already massive black hole. Distinguishing these scenarios requires better data. Higher resolution imaging could resolve spatial structures within little red dots, revealing whether they contain multiple stellar clusters or single point-like sources. Deeper spectroscopy could measure stellar ages and chemical compositions, determining whether stars formed before, during, or after black hole growth. Research groups worldwide are pursuing these observations. The stakes are high. If little red dots represent a new phase of galaxy evolution, textbooks will require major revisions. If they turn out to be rare anomalies driven by exceptional circumstances, their impact on broader understanding will be minimal. LAP-1b's significance partly depends on this outcome. If population 3 clusters commonly evolve into little red dots and then into normal galaxies, finding LAP-1b places us at the beginning of that evolutionary sequence. If the connection is weak or non-existent, LAP-1b remains interesting, but perhaps not representative of how most galaxies formed. Time and more observations will tell. But one particular object has already rewritten record books and raised more questions than it answered. Distance equals time. Every observation of a distant object is a journey backward through cosmic history. The farther we look, the younger the universe becomes. At some point, we approach the absolute beginning, the moment when the first light appeared after the Big Bang. JADESGSZ140 sits closer to that beginning than almost anything else ever observed. Its light left when the universe was only 290 million years old. This corresponds to a redshift of 14 times stretch factor. Light that departed as ultraviolet now arrives as deep infrared, barely detectable even with Webb's advanced instruments. This object should not be so bright. At such an early epoch, galaxies had minimal time to assemble mass. Theory predicted only small, faint systems should exist. JADESGSZ140 contradicts this expectation. It shines with a luminosity, suggesting significant stellar mass already accumulated, perhaps hundreds of millions of stellar masses worth of stars. The discovery came through the JDS program, James Webb Advanced Deep Extragalactic Survey. Researchers targeted specific fields, taking extremely long exposures to capture faint distant objects. When they processed the data, JADESGSZ140 appeared as a bright point of light in infrared filters, but disappeared completely in shorter wavelengths. Initial photometric analysis suggested a high redshift, possibly above 10. Skepticism immediately arose. Previous telescopes had found objects claimed to be extremely distant that later turned out to be misidentified lower redshift galaxies. The scientific community demanded spectroscopic confirmation before accepting such an extreme distance claim. In January 2024, Webb's spectrograph observed JADESGSZ140 for nearly 10 hours. The resulting spectrum removed all doubt. Clear emission lines from hydrogen appeared at precisely the wavelengths expected for redshift 14. Additional lines from oxygen and carbon confirmed the identification. This confirmation established a new distance record. JADESGSZ140 became the most distant confirmed galaxy in the universe. More importantly, it revealed that substantial galaxies existed far earlier than models predicted. The 290 million years between the Big Bang and this observation is less than 2% of current cosmic age. In that brief window, gravity had already assembled complex structures. What makes this object particularly puzzling is its size and brightness. The spectrum indicates it contains not just young stars, but also older stellar populations, stars that formed even earlier and had already aged by the time we observe JADESGS140. This implies star formation began well before 290 million years after the Big Bang, pushing the formation of first stars to even earlier epochs. Scientists estimate that some stars in JADESGSZ140 might have formed as early as 150 to 200 million years after the Big Bang. This approaches theoretical limits for when the first dark matter halos became massive enough to trap gas and ignite fusion. If these estimates hold, we are seeing star formation from nearly the absolute beginning of when it became physically possible. The oxygen detected in the spectrum adds another layer of complexity. Oxygen forms inside massive stars and gets released through supernovae. Its presence means stars had already lived, died, and enriched their environment by the time JADESGSZ140 existed. This entire cycle formation, evolution, death, enrichment, and new star formation happened in less than 150 million years. This timeline challenges understanding. Stellar evolution models predict massive stars live a few million years before exploding. Chemical enrichment and mixing take additional time. Building up detectable oxygen abundances should require multiple generations of stars, which models suggested would take hundreds of millions of years. JADESGSZ140 compressed this timeline dramatically. Either stellar evolution proceeded faster in the early universe, or the first stars were even more massive and short-lived than currently modeled, or multiple generations formed and died in rapid succession. All three possibilities require revising theoretical frameworks. LAP-1b and JADESGSZ140 represent different stages of the same story. LAP-1b shows population, 3 stars in their youth, just beginning to pollute their environment. JADESGSZ140 shows a more evolved system where multiple stellar generations have already cycled through birth and death. Together, they bracket the timeline of early cosmic evolution. But even JADESGSZ 140 might not represent the earliest stages. Searches continue for objects at redshifts above 15, corresponding to times before 250 million years after the Big Bang. If such objects exist, and Webb can detect them, we might glimpse the very first stars igniting in the cosmic dawn. But getting bright enough to detect requires unusual circumstances. Gas turns into stars through a process that wastes most material. Clouds collapse under gravity. Turbulence stirs the gas. Magnetic fields thread through, providing additional support against collapse. Stellar winds from newly formed stars push material away. Supernovae blast holes through clouds, disrupting ongoing collapse. By the time a molecular cloud finishes forming stars, typically only 10 to 20% of the original gas mass has converted into stellar mass. The rest either got expelled, remains as unconverted gas, or dispersed into the surrounding medium. This low efficiency has been measured in nearby star-forming regions and confirmed through simulations. Efficiency matters because it determines how quickly galaxies build stellar mass. Higher efficiency means more stars form from the same amount of gas, allowing galaxies to grow faster. Lower efficiency means galaxies need more time and more gas to accumulate significant stellar populations. Early universe models assumed efficiency would be lower than modern values, perhaps 5 to 10%, because early galaxies lacked the heavy elements that facilitate efficient cooling. This assumption led to predictions that early galaxies would be small and dim, taking billions of years to grow massive. Red monster galaxies shattered this assumption. Spectroscopic measurements revealed these objects converted gas into stars at approximately 40 to 50% efficiency. This is 4 to 5 times higher than modern galaxies, and 5 to 10 times higher than theoretical predictions for early systems. Such high efficiency has profound implications. It means early dark matter halos could build massive galaxies far faster than previously thought. A halo that captures 1 trillion stellar masses worth of gas could convert 500 billion of that into stars within a few hundred million years. This explains why Webb finds so many massive galaxies at early times. The mechanism behind this enhanced efficiency remains unclear. Several possibilities have been proposed. First, early halos might have experienced unusually rapid gas infall, compressing materials so quickly that turbulence and magnetic fields could not prevent collapse. Simulations show that when gas accumulates faster than it can dynamically respond, star formation becomes highly efficient. Second, the absence of heavy elements might have paradoxically helped in certain regimes. While heavy elements aid cooling at low densities, at high densities their cooling becomes less important. If early gas reached higher densities before fragmenting, the resulting star formation could be more efficient, despite lacking metals. Third, feedback mechanisms might have operated differently. Modern star formation is heavily regulated by feedback, the energy injection from stars into their surroundings. If early stars produced less disruptive feedback, or if feedback energy escaped more easily from compact early systems, star formation could proceed more efficiently. Fourth, dark matter properties might differ from assumptions. If dark matter halos were slightly more concentrated or had different density profiles than models predict, gas dynamics would change accordingly. This could affect how quickly gas cools, collapses, and forms stars. LAP-1b provides a data point for testing these hypotheses. Its total stellar mass of roughly 2,700 stellar masses formed from a dark matter halo, estimated at 50 million stellar masses. If the halo captured gas proportional to cosmic baryon fraction, approximately 15% of the dark matter mass, it would contain roughly 7 million stellar masses worth of gas, converting 2,700 stellar masses from 7 million available gives an efficiency near 0.04%. This is far lower than red monsters. But LAP-1b represents a very early stage of star formation. The cluster has just begun forming stars. Most of its gas remains unconverted. Over time, if star formation continues, total efficiency could climb. However, pollution will interrupt this process. As supernovae enrich the environment, gas conditions change. Future star formation will produce population 2 stars rather than population 3. The window for pristine star formation closes quickly. This might limit how much total stellar mass can form before the transition occurs. Statistical studies of many early galaxies are revealing patterns. Smaller systems like LAP-1b show lower integrated efficiencies. Larger systems like red monsters show higher efficiencies. This suggests a mass-dependent efficiency trend where more massive halos convert gas into stars more effectively. If this trend is real, it has important consequences for galaxy formation theory. Current models assume efficiency depends primarily on gas properties, temperature, density, composition. A mass-dependent efficiency would indicate that halo properties also matter, perhaps through their effects on gas dynamics or feedback escape. Confirming these trends requires larger samples. Each new discovery adds constraints. Each spectrum provides measurements. Slowly, the picture is becoming clearer, but clarity brings new questions. One of the most pressing concerns, metal pollution itself. The universe was born sterile. No carbon, no oxygen, no iron, just hydrogen, helium, and trace lithium, created during Big Bang nucleosynthesis. Every other element on the periodic table formed inside stars or during stellar explosions. This means the first generation of stars determined chemistry for everything that followed. Population. 3 supernovae were chemical factories. When massive first-generation stars exploded, they synthesized and ejected dozens of elements. Carbon and oxygen dominated the yields, produced through helium burning in stellar cores. Heavier elements like silicon, sulfur, and iron formed during the final stages of fusion and explosive nucleosynthesis. These explosions did not just create elements, they scattered them across space. Supernova ejecta traveled at 10% the speed of light, plowing through surrounding gas and mixing elements into previously pristine regions. Over time, this pollution spread through entire dark matter halos and even beyond into intergalactic space. The rate of spreading determines how quickly the universe transitioned from population 3 to population 2 star formation. If metals mixed rapidly, the pristine phase lasted only a few million years. If mixing occurred slowly, pockets of pure hydrogen and helium might persist for hundreds of millions of years, allowing population 3 formation to continue sporadically. Computer simulations of this process reveal complex dynamics. Supernova explosions create bubbles of hot, metal-enriched gas. These bubbles expand, eventually breaking out of their host halos and ejecting material into the surrounding medium. Meanwhile, pristine gas continues flowing into the halo from cosmological accretion. The two streams, enriched and pristine, mix turbulently. Simulation results suggest mixing takes tens of millions of years. During this period, different regions within a single halo might have vastly different metal content. Some areas remain pure, allowing continued population 3 formation. Others become enriched quickly, transitioning to population 2. This creates a heterogeneous environment where both stellar populations coexist briefly. LAP-1b appears to be in this transitional state. The detected carbon and oxygen abundances are approximately 1/100th of values found in later stellar populations. This suggests early-stage pollution, perhaps 3 to 7 supernovae, have occurred, releasing their products into nearby gas. The metals are there, but have not yet spread uniformly through the cluster. This low metallicity is diagnostic. If LAP-1b contained metals from dozens of supernovae, abundances would be much higher. The fact that enrichment remains minimal indicates the cluster is very young, probably only a few million years old. Most of its population 3 stars have not yet completed their life cycles, but pollution accelerates. Each subsequent supernova adds more metals. As metallicity increases, gas cooling becomes more efficient. This triggers a feedback loop where star formation shifts towards smaller, more numerous stars rather than rare, massive giants. Within another 10 to 20 million years, LAP-1b will likely transition fully to population 2 star formation. This transition is observable in principle. If astronomers could monitor LAP-1b over time, they would see spectral lines from heavy elements growing stronger as more supernovae occur. Of course, this is impossible. LAP-1b is 13 billion light-years away, and we see it frozen at a single moment. But by finding many clusters at different stages of pollution, scientists can reconstruct the evolutionary sequence. Early surveys are identifying candidates. Some objects show almost no metals, suggesting they are catching population 3 formation very early. Others show moderate enrichment, like LAP-1b. Still others show high metallicity, indicating the transition is complete. By comparing properties across this sequence, researchers can measure how quickly pollution proceeds and how it affects star formation. One surprising finding is that metal spreading might be more efficient than simulations predicted. Some galaxies at redshifts of 5 to 7, corresponding to roughly 1 billion years after the Big Bang show, uniformly enriched gas across their entire extent. This suggests metals mixed thoroughly in less than 1 billion years. If mixing is this efficient, population 3 formation might be rarer and more confined than theorists expected. Only the most isolated, low-mass halos would retain pristine conditions long enough for multiple generations of population 3 stars. Larger halos would become polluted quickly, transitioning to population 2 after just a few supernovae. This makes objects like LAP-1b precious. They represent fleeting moments in cosmic history, windows where the universe was transitioning from its primordial state to the chemically complex cosmos we observe today. But pollution is not the only signature revealing these ancient stars. Their temperatures leave distinctive marks on the light they emit. Light carries information. When atoms absorb or emit photons, they do so at specific wavelengths determined by quantum mechanics. Each element has a unique pattern of allowed transitions, creating a spectral fingerprint. By analyzing which wavelengths appear bright or dark in an object's spectrum, astronomers identify composition, temperature, density, and motion. Temperature particularly affects spectral appearance. Hot objects emit light that peaks at shorter wavelengths. Our star's surface temperature of roughly 6,000 degrees produces yellow-white light, peaking in visible wavelengths. Hotter stars with surface temperatures of 30,000 degrees appear blue-white, peaking in ultraviolet. Cooler stars at 3,000 degrees glow red, peaking in infrared. Population 3 stars should be extremely hot. Their high masses create intense core pressures, driving surface temperatures to 50,000 degrees or higher. At these temperatures, most emitted light comes out as ultraviolet photons capable of ionizing hydrogen. When these ultraviolet photons strike surrounding hydrogen gas, they strip electrons from atoms. The ionized gas, called an H2 region, glows brightly as electrons recombine with protons and cascade down through energy levels, emitting photons at characteristic wavelength. The strongest emission comes from the Lyman series in ultraviolet and the Balmer series in visible light. LAP-1b's spectrum shows intense Balmer emission, particularly the hydrogen alpha line. This emission is consistent with very hot stars ionizing surrounding gas. By comparing emission line strengths and ratios, scientists can estimate the stellar temperature. For LAP-1b, estimates place the effective temperature of ionizing stars at 50,000 to 80,000 degrees. This temperature range exceeds typical massive stars in modern galaxies. Even the hottest known contemporary stars rarely exceed 60,000 degrees. LAP-1b's stars appear to be pushing beyond normal limits, reaching temperatures predicted specifically for massive, metal-free population. 3 objects, but there is something else in the spectrum that has astronomers intrigued. Weak emission from helium appears at wavelengths indicating high ionization states. Helium is harder to ionize than hydrogen. It requires photons with higher energies. Detecting ionized helium implies photons with energies above 54 electron volts are present. Only extremely hot stars produce such energetic photons in significant quantities. The helium emission ratio, compared to hydrogen, provides another temperature diagnostic. When scientists apply standard spectral modeling, they find that LAP-1b's helium to hydrogen ratio requires stellar temperatures at the extreme end of what massive stars can achieve. This is consistent with population. 3 predictions, but would be unusual for normal stellar populations. Some researchers have proposed an additional exotic possibility. If dark stars exist and contribute to LAP-1b's emission, they might produce unusual spectral signatures. Dark matter annihilation creates high-energy particles that could ionize helium more efficiently than fusion-powered stars. This would boost helium emission beyond expectations for normal stars alone. This hypothesis remains speculative. The current data can be explained with conventional massive stars without invoking dark stars. But if future observations detect specific spectral features predicted for dark matter annihilation, such as particular gamma-ray lines or unusual continuum shapes, the interpretation might shift. Another spectral feature scientists are searching for is the signature of pair instability supernovae. These explosions produce distinctive element ratios, particularly odd-even effects, where elements with odd atomic numbers are enhanced relative to even numbers. Detecting such patterns would confirm that the most massive population, 3 stars, are indeed undergoing pair instability destruction, as theory predicts. LAP-1b's current metal abundances are too low to measure detailed element ratios reliably. As more supernovae occur and pollution increases, these measurements will become feasible. Follow-up observations planned for coming years aim to track how LAP-1b's spectrum evolves as its stellar population ages and more stars explode. Each spectrum tells a story. The photons collected by Webb's instruments have traveled 13 billion years, carrying information about conditions in the early universe. By decoding that information through spectral analysis, scientists reconstruct events that occurred when the cosmos was young, but collecting those photons required a cosmic trick that Einstein predicted but might never have imagined would reveal the universe's first stars. In 1915, Albert Einstein published his general theory of relativity, describing how mass warps the fabric of space-time. He realized this warping should affect light's path. Photons traveling through curved spacetime would follow curved trajectories, just as objects follow curved paths when moving through warped space. Einstein calculated that light passing near a massive object like our star should bend by a tiny angle, roughly 1.75 arcseconds for light grazing the stellar surface. This prediction was confirmed during a solar eclipse in 1919, establishing general relativity as correct and making Einstein internationally famous. But Einstein considered this effect a curiosity rather than a tool. He wrote that practical applications seemed impossible. The alignment required to produce noticeable lensing was too rare and unpredictable. Einstein could not have foreseen modern astronomy's ability to survey millions of objects and identify the rare cases where perfect alignment occurs. Gravitational lensing comes in multiple forms. Strong lensing happens when a massive foreground object, typically a galaxy cluster, creates multiple images or distorted arcs of a background object. Weak lensing produces subtle distortions detectable only statistically across many background objects. Microlensing occurs when stellar mass objects briefly brighten background stars as they pass in front. LAP-1b benefits from strong lensing. The galaxy cluster MAX J 416 sits between us and LAP-1b, at a distance of roughly 4 billion light-years. This cluster contains approximately 1 quadrillion stellar masses worth of matter, most of it dark matter. This tremendous mass creates significant space-time curvature over a region spanning millions of light-years. When LAP-1b's light passes through this warped region, multiple effects occur. First, some light that would have missed Earth entirely gets redirected toward us. This increases the amount of light we receive, making LAP-1b appear brighter. Second, the image gets magnified, stretched by the lensing effect. Third, the image might appear distorted into an arc or ring shape depending on alignment. For LAP-1b, the magnification factor is estimated at roughly 100. This means the cluster makes it appear 100 times brighter than it would be without lensing. Given that LAP-1b would be approximately 25 times fainter than Webb's detection limit without magnification, the cluster made the difference between invisible and observable. Einstein rings represent a special case of strong lensing. When alignment is nearly perfect, background source, lens, and observer forming a straight line, the lensed image appears as a ring of light surrounding the foreground object. The ring's radius depends on the lens mass and the distances involved. For galaxy cluster lenses, Einstein rings can be several arcseconds across. LAP-1b does not form a complete Einstein ring. The alignment is close but not perfect, so the image appears as a bright arc rather than a full ring. This is actually advantageous for study because the arc can be resolved and analyzed, whereas a complete ring's light would be more blended and harder to interpret. Gravitational lensing surveys have become powerful tools for studying the early universe. Astronomers target known massive clusters like MACS J416, taking deep images to search for lensed background objects. The clusters act as natural telescopes, revealing faint, distant sources that would otherwise remain undetectable. Dozens of massive clusters have been surveyed this way. Each cluster provides a different magnification map depending on its mass distribution. By comparing detections across multiple clusters, scientists build statistical samples of early universe objects and measure their abundance. This technique has limitations. Lensing is not uniform across the cluster's field of view. Magnification varies by position. Some areas provide strong magnification, while others provide little or none. This means surveys only sample the regions behind clusters, which might not be representative of the general universe. Additionally, lensing introduces uncertainties in measuring source properties. To determine an object's true brightness, size, and structure, astronomers must model the lensing effect and remove it. This requires detailed understanding of the cluster's mass distribution, which itself must be inferred from observations. Errors in the lens model propagate into errors in source properties. Despite these challenges, lensing remains essential for studying the faintest early objects. LAP-1b would be completely invisible without MACS J416's assistance. The same is true for hundreds of other distant galaxies and star clusters discovered through lensing surveys. As Webb continues observing and as analysis techniques improve, lensing will reveal even fainter, more distant objects. But finding one population, 3 cluster, raises an obvious question: how many more are out there?